Okay, so hi everyone. My name is Tiago. I am a PhD student at the University of São Paulo. I'm really glad to show this work to you today. And I will show you how we are using simulation to find microstructures for gem optimization. This work is part of a collaboration between the University of São Paulo and the University of Nottingham. And the team leader of the Brazilian group is Thiago Silva, also my advisor, and Gustavo Trindade is the leader of the England team. Can you next slide, please? So first, a really quick introduction of the gas electron multiplier. It's a thin foil with a microscopic hole. This foil is composed by insulated in the middle and clad in both sides with conductive foil. Next slide, please. And how it works is we place this foil inside a gas medium, and an incident particle that enters the detector will form a ionization, a primary ionization. The electrons produced by it will be guided by a drift field to these holes. And between the electrodes of the gem, we apply a high potential difference. This will produce a huge electric field inside of the hole and start the avalanche process that multiply these initial electrons. After the electrons produced are collected in the readout plate at the bottom, and the amplified signals are read. So next slide. This is a picture of Fabio Sauli, the creator of these detectors, holding a foil made for a CERN detector. So next slide. And we are trying to, in this collaboration, we are trying to 3D print this kind of detectors. And how can we produce such small scales holes? So the first thing that we needed to do is find a suitable technique for this kind of, for the resolution constraint that we have. Nowadays in 3D printing, for choosing these techniques, we have to find a balance between resolution and production volume. Increasing one means that we need to decrease the others. So we have available to us techniques like extrusion in the right, where we have a high production volume, but not as good resolution. 200 microns is not enough for the kind of things that we want to fabricate. And in the other end, in the left, we have this 2-photon polymerization with this incredible resolution of hundreds of nanometers. But we are only able to produce samples of 2 by 2 millimeters, which is really small, even to handle. So in this project, we choose that microstereolithography, that PUSLA, and more or less in the middle of this scale, and that provides us with a few microns in resolution and a production volume of 2 by 4 centimeters, which is small for a large detector, but is enough for test and prototype. So next slide, please. And why we are trying to 3D printing these detectors? And the answer is the fast prototyping that the 3D printing allowed us. And what we are aiming here is shown in this cycle. We want first start by designing, using simulation to find new geometries, new candidates for production. We send these designs to prototyping, and later we test it in the characterization step. We test it experimentally, and whatever the results, we use to update the designs, and the cycles go on. And this kind of cycles is only possible if we can go fast from design to prototyping, and that is where 3D printing came in hand. So next slide. But 3D printing is not suitable for mass production and cannot beat standard fabrication techniques in that matter. So whatever the outcome of this cycle, we need additional research to mass production. So can you pass to the next slide? And here I'm showing you the first test that we did. This is only the insulating part of the gem. And this test show us two things. First, yes, indeed, we can print such small holes using this technique. And second, we need to study this. In second, we see that the resolution causes some artifacts in the final product. As we see around the hole, that's this undulation caused by the resolution, the planar resolution. And inside of the hole, in the inner wall, we see these step-like structures. This is caused by the Z resolution, or the layer thickness, because the printing is done layer by layer. So in this case, we have a conical hole, such that each layer has a different diameter, and we see this kind of effect. Can you pass, please? Well, with this first test, we were able to measure that resolution and get 2 micrometers for the planar resolution and 3.8 microns for the layer thickness, which is pretty good. And we are able to have some flexibility in the designs. Can you pass? So, well, that test raise a question, if that artifacts that we see it can affect the performance of the gem. And to test it, we done the simple model where we place that discrete radius inside of the hole in our models, as you can see the red arrow. And can you pass, please? And we done simulations with and without these resolution structures. So in the upper graphics, we have the results with for a standard gem without the resolution artifacts, and in the bottom with the resolution artifacts. So what this graph means. Each point in these scatter plots, it's a point where occurred ionization of the gas, and the electron ion pair was produced. And for the graphs in the left, we have the colors represent the destination of the ions produced. In blue, we have the ions that go up and escape it from the hole. In orange, the ions that hit the upper electrode of the gem, and in green, the ions that get trapped inside of the hole and stick in the insulating material of the gem. In the right, we have the same thing, but for the electrons, because of the electric field, they go downwards. So the blue are the ones that were extracted and collected and formed the signal. The orange, the ones that hit the lower conductive layer of the gem, and again in green, those that get trapped inside of the hole. Can you pass, please? The great difference, the biggest difference between the standard and the printed is the amount of ions, the green ions, the ones trapped. Well, these ions will stay in these inner walls, and with time they will start to build up and charge the detectors, and this can distort and will distort the electric field and change the gain of our detector. So higher amounts of these ions can lead to gain instability, which is not great. But the increase is small, and we don't think that will impact the final the detectors produced by it. But we need to test experimentally to see if if it is true. So next, can you pass, please? And apart from doing this kind of test with simulation, we are also trying to find ways to optimize the gem by inserting small structures around the holes in that we call decorations. At the left, we have a standard gem, and in the left, we add these ring-like structures. Can we pass, please? And the effect of this ring is that it constrains the ions from going further and hit further in the conductive layers, as you can see in the graph. And it acts like a barrier, and we hope that it can reduce the time needed for the absorption and the neutralization of these ions. So can we pass? Another possibility is change the hole and change the decoration. Here we use a conical hole, and we add also a chamfer-like structure. As we see how the avalanche evolves in time, and the ion backflow that it produces. And the ions are in red, the electrons are in blue. Can we pass, please? And the things to note in the simulation is that this conical holes compared to a biconical, more standard one, has a higher gain, but a higher instability also. So in the left, we have in blue, we have a comparison of these conical holes with the standard one, the biconic, and we see that we can achieve 2 times. We can see that the gain is 2 times higher for this kind of hole. But in the left, we have that charge up effect that I talked earlier, and it's also 2 times higher. The amount of the proportion of the charge that getting trapped is it's doubled also. But with the addition of this chamfer, we don't affect much the gain, as we see in these green bars, but we're able to reduce a lot of the amount of this trap charges. So we could, in principle, use this high gain without sacrificing much the stability of the detectors. So can you pass, please?
Tiago, 2 minutos.
Yeah. Oh, well, this is the last example that I want to show you. This is now a cylindrical holes, and we are trying to apply this decoration in both sides, the ring one. And again, the great difference was in this trapped charged particles that stick in the inside the hole. Can you pass? And here we are comparing the gain again and the amount of this charge up effect. And we see that adding in orange is the gem with the decoration. We reduce a little the gain, but it stay more or less the same of a standard one, but we're able to decrease a lot of the charged particles inside of the hole. Can you pass? So to conclude, I show you some of the possibilities of combinations and whole profile and decorations. As you can imagine, many more are possible and many more are under test and study. And here we see that with the simple structures, we were able to change the ion distribution and the charge-up effect, but many more things can be searched, as the effect on ion backflow, collection, extraction efficiency, and so on. I also talk mostly of the simulation of this collaboration. And in the first test, we see that the printing, we are able to achieve a resolution of more or less 3 microns, which is enough for us. But the question that we needed to answer now is how we can deposit the conductive layers in both sides of this dielectric. And I want to do an invitation. My advisor, Thiago Silva, will talk more about this collaboration concerning the printing part today, this afternoon. Today, this afternoon at 11. And that was all.
Thanks a lot.
Thank you very much for.
Thanks a lot, Tiago. Nobody ask question in the chat, but let's raise the hand or ask by voice if you have any question. Waiting for outside question. I have one. What's the plan for experimental verification of this new idea?
Well, the idea is to perform the same test that we do for standard gems. We want to produce both the standard ones and the modified and compare them and see if we can achieve different results with it. So with gain, with ion backflow, using the same measure that is done for the standard version.
No question? If you are not question, okay.